Okay, class. Greetings from the mountains of Montana. The TAs are here and they'll periodically stop to explain things and answer questions, so they can pause this video, which I will have put up on YouTube and ready to go. The learning objectives for today are to finish talking about one-dimensional defects, such as edge and screw dislocations. We'll talk about two-dimensional defects, like stacking faults and twinning. We'll then differentiate between grain boundaries and domains, and finally, we'll describe some of the microscopy techniques that are available to analyze these sort of defects that are available in materials. And then the second half of class will be starting Chapter 7, and we'll describe the learning objectives then. So when we left off last time, we showed you this picture of this bubble raft, and we showed you that if you looked closely, there were these dislocations. There was a dislocation here, right? Which you could best see by drawing lines, right? So if you draw these lines, they looked just fine, except that we had one extra row stuffed in there. And if you notice, as we move further and further away, drawing these lines, there's less and less distortion the further and further away we get from the dislocation. Or in other words, the strain field associated with the dislocation is largest the closer you get to the dislocation, and the further you get away from it, the more it looks like it's not there. And that'll become important later on. Okay. So there's actually two different types of dislocations that we can have in a material. We can have what's called an edge dislocation, or we can have a screw dislocation, right? Both of these have a Burger's vector. Again, our Burger's vector is the value by which, if you do the Burger circuit going around the dislocation, it's how much you would need to add to get back where you started, right? In this case, which we call an edge dislocation, the Burger's vector, which we use the letter B and we put the vector hat on it, it is perpendicular to the direction of the dislocation. So the dislocation direction, it's running up and down in this, say, cylinder that's here. So it's running up and down or along the Z direction. But the Burger's vector, in this case, it's drawn along the X direction, which is orthogonal to the Z direction. Now you can also have a screw dislocation. In a screw dislocation, you can have the exact same Burger's vector in terms of length, but its orientation is no longer perpendicular. In a screw dislocation, the Burger's vector is now parallel to the dislocation direction, right? So in this case, the dislocation direction is running up the Z direction as before, but now our Burger's vector is going up in that direction as well. It's parallel to it. And I think the easiest way to think about a Burger's vector and the screw dislocation is to consider a parking garage. You start down here at the lower level of the parking garage and you do a loop, and by the time you get back to the spot where you were before, you're standing right above, one floor above the spot where you were when you began, right? Or if you go the other way, you're one floor below. So that's what a screw dislocation looks like. And I'm going to have the TAs bring a model that you can actually come and take a look at this. And again, you'll notice that the distortion is most severe right about the center of the dislocation, right? The center of this dislocation that runs from point A to point B in that figure. The strain, right? The stretching of the bonds is most severe closest to that, and the further away you get from it, it's less and less severe. Okay. So that's the Burger's vector, that's edge and screw dislocations. And again, you can see these all over the place. In corn, right? You can see an extra half row. It's right there. They're all over the place. So again, this is us looking down along a Burger's, an edge dislocation, right? In this extra half row of atoms is visible there. Now, dislocations do not have to be either screw dislocations or edge dislocations. They can have mixed character, right? The same dislocation can actually change direction. It can start out as an edge dislocation, but by the time it gets over here, it's now a screw dislocation in the lattice, right? Because the Burger's vector right here, that thing pointing to the left and this thing pointing to the left, it has not changed anywhere, right? It's just that the dislocation has done a loop here. Okay. Now these dislocations are important, and we will come back to them in Chapter 8 when we talk about deformation mechanisms. Basically, the ability to have a dislocation and to have that dislocation move through a material is how we achieve deformation, right? So this extra half row of atoms, it could start right there, and if you apply a force on this thing, if you're pushing it here, a shear stress, and you're pushing it down here, that might move to over here, and if you keep pressing, it might actually pop out at the end, and you can achieve macroscopic deformation by the movement of many of these dislocations. So we will come back to that. Let's now shift gears and talk about two-dimensional defects. These are sometimes called interfacial defects, right? So examples of these are the grain boundaries and the surfaces that we've been talking about in class, therefore the surface energy. And I think this is most easily seen if you look at a crystal. There's regions of this which are very nicely aligned. You can see that this is a nice sort of cubic arrangement of atoms. However, it runs into a different cubic arrangement which has been rotated slightly, and so these things don't match up. Similarly here, this thing doesn't quite match up. This one's not quite matching up, and it's a smaller lattice, right? So where those things come together, you're left with a bunch of what we call grain boundaries. So along here, grain boundaries, you can see them throughout this material, right? If you look closely, I'm sure I've missed a few, but that's roughly where the grain boundaries are in this material. And again, grain boundaries represent regions where atoms don't have their optimal bonding arrangement. In the center, this thing is happily bonded to the 4 atoms adjacent to it. But if you look at this atom, it's far too close to the 4 atoms around it, right? Whereas this one doesn't even have the right number. It sort of has 4 or 5 or 6, depending on how we would count these things closest to it. It doesn't have the right number of bonds. And so along grain boundaries, you always have regions of higher energy because of dangling bonds or too many bonds or stress or atoms being stretched. And so these all cost energy. And so we typically talk about them with having an energy in joules per meter squared is typically how it's done. Okay, so grain boundaries are the first type of two-dimensional defect that we're going to talk about, but there's other ones. So for one thing, with grain boundaries, you can think of them as a series of aligned edge dislocations, right? So again, here's our grain boundary separating two different crystallographic orientations, and if you look closely at it, if you were to zoom in on that, you see this little T symbol. The T symbol represents an edge dislocation, where this is the extra row of atoms. So that is an edge dislocation. Right? And basically the angle of this will dictate how far apart these things are separated. Right? So they could be separated, as you can see in this figure, about that far apart. There's your extra half row of atoms, your extra half row of atoms, extra half row. And that separation is going to be proportional to the angle separating these two lattices, right? So these two lattices are separated by an angle theta, right? This angle to that angle, excuse me, let me redraw that, to this angle, that is theta degrees. So the separation distance, which we could call d, for example, that mathematically you could calculate from the Burger's vector, b, up here, and the angle, right? If you do the math, you'll find that that d, the separation between those, is just the Burger's vector divided by the mismatch between those two orientations, theta, right? Sometimes we call that the grain boundary angle. And again, how we know that is you're basically drawing a triangle like this. This is b, that length there is b. You're calling this d, right? And you know that this is theta. So to figure out the distance between those, we take advantage of the fact that the sine of a small angle, theta, is approximately just equal to that angle. And that's what allows us to write that d is equal to b divided by theta. Okay, that's grain boundaries. Now somewhere else earlier in the class we talked about, what if you had a really big atom, something that was too large, and it's right there, and it's squeezing the neighbors around it, right? Well, this atom, it can choose to move. It doesn't have to stay there. If it has some thermal energy, it can move. And where is it going to move to cause less stress, to crowd its neighbors a little bit less? Well, it might choose to move right there, right? In that spot, just above it, it's crowded because it's got the extra half row of atom. But that crowding stretches this bond, right? So right there is actually an ideal spot for a large impurity atom to migrate. So it's going to migrate to the grain boundaries, and in many cases they settle at the bottom of these dislocations. And again, if you had a small impurity, something that was too small, and so it wasn't big enough and it was causing strain because it wasn't large enough, it might migrate to just above that dislocation where it was crowded, and so a small atom is actually welcome there because it's going to reduce the strain from the dislocation. So because of that, you get impurities traveling to these grain boundaries. Now, other types of interfacial defects are available in crystals. One of them is called a twin boundary. And a twin boundary is really just a special type of grain boundary where you have mirror symmetry, right? So these planes, right there and right there, these things have mirror symmetry. This atom is reflected onto that one. This atom reflects over here, right? So it's just mirror symmetry. So it's a specific type of orientation that preserves this. Again, this would reflect over that. This would reflect over to that. Has mirror symmetry. So these would be called twin boundaries. They are still dislocations, right? The lattice loses its nice orientation that it liked to have, you know, over here. It's now mixed. It's been rotated, and the regions on the vicinity of the twin boundary are messed up a little bit. So it does cost energy, but it's a different type. Well, it's a special type of grain boundary, you can say. And there's other ones. There's also stacking faults. If we go back to our crystal structures, FCC and HCP, these could be thought of as different stacking of layers, right? So remember, we had the tennis balls, and if you were to stack these tennis balls, you could stack them like so. And when we start our next layer, when we choose where to put our next layer, we can choose to put it on the triangle up or the triangle down. This is what I mean by the triangle up. That triangle up or that triangle down. So if we set our next layer on the triangle up, we can draw it as so. Right? You can add layers and layers. So the red layer might be layer A, the blue layer might be layer B. And in the FCC lattice, we know that it stacks ABC, ABC, ABC. It keeps on alternating. But it can also get messed up. Instead of going ABC, 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 it could do something else, right? Here it goes A, B, C, A, B, but instead of going to C, it goes back to A. And then it goes A, B, C, A, right? So there's a missing C layer there, and that causes a slight mismatch along this dotted red line there, which we call a stacking fault. And again, it's just locally that the atoms aren't quite arranged in their most optimal way that they could be, and so they cost a little bit of energy due to that. Again, you can see kind of what happens there. Here you have, so you've got A, B, C, A, B, C, A, B, C. So on this side, on the right-hand side, all of this, it's normal. But here you're going to see where it inserts in it and it messes it up. You've got A, B, C, A, B, A, B, A, B, C. Right? So it breaks it up and it causes a slight dislocation. And along this interface, you see that the bonds get stretched. Now, apart from stacking faults, you can have phase boundaries. So in an alloy, if the two different atoms are randomly placed wherever, we call that a random alloy. But they might choose to actually orient themselves and actually segregate, right? If it's causing too much strain in the lattice for them to be just mismatched everywhere, they can choose to segregate. So you see here that these atoms have segregated to a different lattice, and it actually has a slightly smaller lattice constant than the white atoms, right? They can also be organized. So example, in this case, you see that the black and the white atoms have formed an ordered compound and are existing there. And the lattice parameter more or less matches the lattice parameter of just the pure white atoms. And again, the more mismatch along these boundaries, the bigger the energy penalty associated with it. So these are grain boundaries. You can also have domains. Domains are different than boundaries, right? Domains can be the same, but they can also be smaller. Domains have to do with a property of interest. That can be a magnetic domain, right? Some region of your material which is aligned magnetically in a certain direction. Or it could be electric, where there's a polarization, and we'll talk about these later in the semester. But for now, we're just going to say that domains are another type of region, and it can have an interface just like grain boundaries. Okay, the last type of defect we're going to talk about is three-dimensional ones, and these are typically large-scale things like cracks, pores, inclusions, a big second phase or something. So that goes from 0, 1, 2, and eventually to three-dimensional defects. So then the question might be, how do we actually visualize these things? How do we observe these defects in materials? So you can look at it with your eye, but your eye typically has the resolution around 50 microns. If you're young and your eyes work great, maybe you can see down to 10 microns. Just to give you some context, a human hair has a diameter around 10 or 20 microns, I think. So you can't see a lot smaller than that. And yet some of these defects are going to be far smaller than that, so we need a better way to look at them. So the first thing we could use is an optical microscope. An optical microscope uses light that we can visually see with our eyes, and it uses lenses. And by using those lenses, it can achieve magnification, right? Now the challenge is that for opaque materials like metals, right, that aren't transparent, you're only going to be able to look at the surface. You won't be able to look anywhere else, right? And one of the things that you can do with these is we often use them in reflective mode, where light is brought in, right? Here comes your incoming light. And then it's going to interact with your material in some way. It's going to bounce back, and you actually observe the reflected light is what you're looking at. And your material, if it's oriented in different ways, right? So this material might be oriented with grains like that, and you might have a different orientation right here, and yet a different orientation there. Light will interact with those orientations in slightly different ways, where some of the light, like more of the light might bounce back this way, a little bit less bounces that back that way, and even less of the light is reflected back to the lens when you do it in that way. And therefore, the same material, even though it's all, say, pure copper or pure aluminum or whatever, it can still have different contrast. You can have really bright, medium, and really dark, right? So this is different grain orientations, which makes it able to achieve contrast. It makes it really easy to see different grains. And the best way to do this is you can do etching, right? You can etch these things to preferentially form these grooves along certain crystallographic directions. So adding a little bit of acid or something can really make these different grains easy to see. Okay, so with optical microscopy, you're only going to be able to see, at the very best, like with really the best tools out there, maybe down to 200 nanometers. And that's really a stretch even. And that's about 2000x magnification. So let's move to electron microscopes. Electron microscopes are fundamentally different. Instead of using visible light, which our eyes can see, they say, well, one of the problems with trying to see smaller than visible light is that light has a wavelength of 390 to 700 nanometers. And so it becomes very hard to visualize objects that are much smaller than the wavelength of your light. If the feature that you're trying to look at is that big and your light... So trying to visualize objects smaller than the wavelength of light that you're using becomes impossible. Therefore, if you're trying to look at things much, much smaller, you need to use a much, much shorter wavelength of light. And if it's smaller than what our eyes can visualize, we need to use a different detector. We need to use an electronic eye, right? A detector that can pick up that light. So that's exactly how electron microscopes work. Instead of using visual light like photons, they use electrons. And they accelerate electrons to such a speed that their wavelength becomes very, very small. It becomes small enough that you can visualize very small objects. So for example, the wavelength of some of these electrons is as small as 0.003 nanometers. So extremely small, 3 picometers. Right? Because of the small wavelength, we can achieve extremely high magnifications and resolutions. And since you're basically sending electrons, you're starting with electrons and you're sending them down a tube towards your sample, you have to have a series of magnets and condensers and apertures to try and focus that electron beam down along your sample. And it rasters along your sample. So if you're looking at the surface of your sample from above, it rasters along it like a TV. It just goes line along line, goes along like this, and then it starts over back to the top again. And that's how you generate these images in these electron microscopes. So the first type of microscope we're going to talk about, the first type of electron microscope, is a transmission electron microscope, or a TEM. And in this case, the electron beam actually goes right through your sample, right? So again, if your sample would be right here, and then you have a big detector plate down here. So the electron's going to go down through, and you're going to pick up the signal that way. Therefore, your sample, since you're requiring that electrons pass right through your sample must be very, very thin. In fact, a lot of work has to go into preparing your sample to get it thin enough that the electrons can go through it without being just completely absorbed. What's also great about that is since electrons can have a wavelength similar to the separation distance of your atoms, you can actually also get diffraction, where these things now get split in different directions, and you can use that information to figure out phases. It's just like Bragg's law, just like we talked about before. You can get diffraction, and you can solve for different crystal structures by doing this. So using transmission electron microscopy, you can achieve up to 1 million x magnification, so just an enormous magnification is possible. And I hope it's startling you that in this picture, which we have from a TEM, you're looking at atoms in graphene, right? This is the graphene molecule, and you're seeing individual atoms. And the fact that we can do that is just mind-boggling, absolutely amazing, right? And then a more common type of electron microscopy, certainly something that's far less expensive, is scanning electron microscopy. And in this case, You don't accelerate the electrons with such a high voltage, and you don't have to look at it by traveling through your material. You can just hit the material surface, and it looks at electrons that are then reflected, or secondary electrons, ones that are generated within your material. So again, if this is the material that you're looking at, you're going to bombard it with high energy electrons, and then you're either going to see these things bounce back, or you're going to generate a secondary electron. Right? You can either look at the primary electrons, which are bouncing back, that's called backscatter mode, or you can look at secondary emission, right? So secondary electrons. Either of those works, and just like before, it's going to raster, and just like an old TV, it'll raster to create these images. Since you're bombarding this with electrons, you do have to make sure that your samples are electrically conductive, and if they're not, they typically put down a metal coating like gold. They coat it with a little bit of gold or something to make sure that it's conducting. And with this, you can achieve, less than the TEM, but you can achieve up to, 50,000 x magnification. And what's great about this tool is that you have a really large depth of field, meaning that both things that are far away and close together can both be in focus. So here's some images that I took when I was an intern, 10 years ago on an SEM, looking at bugs late at night in the laboratory. You can see along the fly's eyeball or on its legs or along the wing. Here's a spider's eyes. There's groups that have what's called cryogenic SEM or TEM, where they can actually look at snow crystals of ice forming, because they can freeze them inside on the sample holder. You can do really cool fractography. Here's an example of a screw. They're looking right at the fracture surface, trying to see where the crack originated, what sort of things happened as it moved through and broke in the material. And then the last thing I'll talk about with electron microscopy is that it is well suited for elemental analysis. We've already talked about energy dispersive spectroscopy, and an SEM allows you to do that. Again, this is your sample. You bombard it with a very high energy initial electron. An atom has its nucleus, and it has its different atoms around it. If you knock out this electron, then this electron is going to fall down to fill its place, and in doing so, it's going to give off radiation. And all you need to have is a detector that can pick up that radiation and look at how much different signal is coming at different wavelengths, match that to the elements, and then by doing that, you can generate an enormous amount of information. Take, for example, this image right here on the left. This is your just regular secondary electron sample. Basically, you're taking energy. You're taking the electrons, you're bombarding it, it's generating other electrons, and you're using it to visualize it. And it basically just looks like a gray mass. You can see that there's another region there, but it's hard to see much else. If you switch to backscatter electron, you generate this image. Backscatter, again, that's when you look at how many samples bounce right back. So high density elements, things with a higher atomic number, they're going to bounce back more than the low density ones. So you can see right away that this trapezoidal region here, that must be an element that's higher in atomic number than the gray region around it. And now you see that there's these really dark regions which must be even a lower atomic number, because less is bouncing back there. And then when you couple this with EDS, you can now see right away that, okay, this region right here, that's sulfur. You can see other things that, let's see, that also had iron in it. Looks like it was rich with iron and sulfur, so it's probably some iron pyrite. Whereas the rest of it, this is magnesium out here. Looks like it's oxygen, a little bit of manganese. So it's a really useful tool for figuring out what is there. So if you had a material that failed for some reason, you can do some really interesting diagnostic work to figure out why it failed and what were the sort of impurities that were there. Now, the last type of analysis tool that I'm going to talk about just briefly is scanning probe microscopy. And the most common one is an AFM, or an atomic force microscope, and it works just by tapping a little sensor along a material. This sensor is right here. You want it as sharp as possible. That's going to tap along, right? So you have this little cantilever, and there's your tip, and this is the surface you're trying to examine, and this is just going to tap, 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 and it's going to measure how far it can go down before it touches the surface. And using AFM, you can actually look at individual really interesting molecules and match what you're actually looking at, and they've done some pretty amazing things with microscopy. So that is, let's see how we're doing on time. We got a little bit left. So let's move on to chapter 7 now. So chapter 7, here's our learning objectives. The first part is we're going to review basic stress and strain, including engineering versus true stress and strain. Right? This is stuff that you've probably seen in another class, so we're going to go briefly through it. We'll then talk about Hooke's law to talk about how much strain occurs for any given stress. We'll talk about key factors like the yield stress, proportional limit, tensile stress, toughness, resilience, and if we have time, we'll get to Poisson's ratio. Okay, so up till now, we've talked about defects. We know that they're there, but we haven't yet talked about what they do in terms of mechanical properties. How do they affect them? So before we do that, let's talk about mechanical properties of the undefected materials first, right? And obviously this is really important as engineers. Half of the things we do are trying to prevent failure or to make things fail in a certain way that's as safe as possible, right? Whether that's a car crash or whether that's pressure release valves, we need to understand how forces interacting with material can lead to them eventually breaking. Okay? So questions we're going to try and answer this chapter are just how strong are materials? How much can they deform? Is it reversible, right? If deformation occurs, can we undo it? Is it different for different materials? And then is it necessary to test the strength, hardness, right, under different conditions, right, in terms of time, environment, temperature, cycling, etc. And with that, I'll just give a quick plug for the ASTM. Basically, if there's people all around the world all doing materials testing, how do we make sure that we can compare, say, a yield strength for an alloy that's measured here in our lab at the University of Utah with somebody who does it over in Germany, right? The way that we do so is we all adhere to the ASTM. The ASTM is a series of standardized tests for doing pretty much anything you can imagine. If there's something that you'd like to measure, whether that's the friction of skis on snow or whether that's paint peeling off of a water tower, there is an ASTM for that, which will describe exactly how you perform the experiment, how you quantitatively measure the property of interest, and so they're great ways to go. And so as engineers, it's important that you don't just come up with some random way to test things, because that will only be able to compare with things that you've tested in that same random way. It's far better to test them in a way that everyone will be able to relate to and compare with. All right, let's start with types of loads and forces. If you're just pulling on something, we've been calling that tension in this class. Now you pull with a force F. F is the load, right? This has a cross-sectional area, A. So the first thing to note is that the stress is equal to the force divided by the cross-sectional area, right? You don't have to just pull things apart, though. You can also squeeze them. You can push down, right? The force is going to be equal and opposite on those two faces, but so we define the difference between those with just the sign. In this class, we've been saying that a positive force leads to a positive stress, we call that tension, and a negative force leads to a negative stress, and we call that compression. But there's in both these cases, the force is being applied normal to the face. The force is being applied normal to the area that's acting on. If the force is being applied parallel to it, right? In this case, imagine this block here. If you were to take your hand on that cube and you're trying to just smear it to shear this thing, we call that a shear force. It's no longer tensile or compression, and it doesn't create just the elongation or the contraction. It creates this deformation, which is shear. It shears it, right? So again, it's equal and opposite forces. You've got one force acting along that surface and one force acting along that surface, and it creates this shear. And we can measure that with the shear angle theta there. And then torsion is just a special type of shear where one end is fixed and you're also bending it. You're applying shear on the other end, right? So one of the most common ASTM tests for measuring tension, for testing a material under tension, is with a dogbone test. The reason that we do dogbone tests is the following. It has a specific shape that allows it to break in the center. You typically have clamps that you're going to grab onto this thing right here, and right here you're going to clamp onto it. And the clamps have little teeth that bite into the material. So what's happening is everywhere those teeth bite into your material, it's actually weakening the material right there, and you don't want it to break due to how you clamped onto it. So because of that, they make it a little bit more narrow. You see that this is necking down here and necking down. That makes this cross-sectional area here in the middle smaller. And again, because force is equal to, stress is equal to force over area, by making the cross-sectional area smaller, you increase the stress. Therefore, you increase the likelihood of it failing in the center. These can be either clamped on or you can also screw them in. That design also works, right? During these tests, they simultaneously measure both the load, or the stress, right? They measure the load and they turn that into a stress. And then they also measure the strain. And I'll remind you that the strain is just the elongation divided by your initial length, right? So epsilon equals your instantaneous length divided by your initial, minus your initial divided by your initial, right? Or delta L over L. So we can introduce engineering stress and engineering strain to remove the geometrical factors in real time, right? So the true stress and the true strain is different than the engineering stress and strain, because your material, as you start to pull on it, right? If you start out with a material that looks like this, and as you pull on it, it's going to shrink a little bit in cross-sectional area, then the area here, that area instantaneous, is not equal to the area initial, right? The instantaneous area is not equal to your instantaneous area. So to account for that, we have engineering stress versus true stress, or engineering strain versus true strain, and we will come back to that a little bit later. The units that we typically use for this force, we're going to use newtons. Area, it doesn't matter, we're going to use meters squared. And then stress is going to be if you use newtons per meter squared, that equals a Pascal. Or if you do newtons per millimeter squared, that's equal to a megapascal. Right? Now strain, note that it has no units, right? This is the difference between L naught and Li, that's just a distance divided by a distance, so it has no units. Sometimes it's given as a percent or even as a ppm, as a parts per million. Okay, we can skip some of these definitions. If you have a material, let's say you had a cylinder, at some arbitrary imaginary plane in this material, right? It doesn't have to be like a real interface. You can just pick any plane. Even though you're pulling on this, let's say, with a force, and it's acting on this area, along this plane, we can actually figure out what the forces are in arbitrary directions. We can figure out what is the normal force to that plane and what is the shear force acting in that plane. The shear, I guess we should say the normal stress and the shear stress acting on that plane. And they're going to depend on this angle that this plane is rotated at relative to the applied force. We'll come back to that in a few chapters when we talk about deformation mechanisms, but here's what these values come out to, the expressions for those, and you'll see that I think in this homework this next coming week. Okay, I think the last thing that we have time for, is elastic deformation. So here we're going to talk about Hooke's law. Hooke's law tells us how the stress and the strain are related. So if you apply a stress to a material, say 10 megapascals, how much strain will that produce? Well, the amount that it will produce is proportional to capital E, Young's modulus, which we've described earlier in the semester, right? That's the constant in proportionality when we looked at our force, interatomic force versus interatomic separation. We said that there's this curve right there, and this was the point at which there is no net force. We said that it was proportional to that. Basically, if you apply a lot of force, if it takes a lot of force to achieve a small change in R, then you had a very stiff material. Okay, so when you plot stress versus strain, which is the typical way of showing these materials, you'll have usually straight lines. They don't have to be, but they're often straight lines with different slopes, right? These things have different slopes. Now, these correspond to different materials. So you might ask yourselves, which one of these materials is the ceramic, which one is the polymer, and which one is the brittle steel in this case. So go ahead and take you can pause the video here. I think we're going to end it, and you can discuss which one of these things it is, and we'll pick up here next time.